Now we are going to solve the differential equation for an air circuit that has a alternating current instead of direct current as we did in the previous video. So again we have the resistor, the inductor, and here we have a alternating current. The voltage is alternating. So the let's say this is the positive end, the negative end. The closed loop integral of E dot dl is equal to Faraday's law, not Kirchhoff's loop rule, of the negative change in the magnetic flux with respect to time. This is just the negative of the self-inductance, the I in dt. And this would be the closed loop integral if we start from here all this way would be E dot dl would be the current times R. Here we have 0 and here we have a negative voltage because we're going in this case from negative to positive as opposed to positive from negative. That is the opposite direction of the electric field. Going from negative to positive is the opposite direction. This is equal to the negative L di in dt. We can rearrange this to have a first order differential equation that is di in dt plus R over Li is equal to the voltage divided by L. Now here the voltage, I would say that the voltage is a function of omega of theta. I would say the voltage is equal to some original voltage times the cosine of omega t. Remember that omega t is theta in the case that theta is equal to theta original plus omega original t plus 1/2 of the angular acceleration times the time squared. We have 0 acceleration. That is a we are talking now about a steady current, not exactly at the time in which we turn it on, because at that time yes, we have a acceleration, and this is 0. So we have theta is equal to omega t. So for that I write it like that. So I would say here I have instead of b I would put v sub naught cosine of omega t. We solved this many videos ago, well, in other playlist. When we deal with differential equations, we call that video something like integrating factor for solving equations with applications to life or something like that, and we divide it in when we did integrating factor, then we take a Cartesian wave and a polar wave in separate videos. That is the same thing that we're going to do. So first, this is the first order differential equation. We need to take the integrating factor. That is a very useful trick. So the integrating factor would be e to the integral of R L over L dt. That is just e to the R e t over L. So let's multiply everything by that. I will do it here. I have e to the R over L t here plus e to the R over L times t, and here e to the R over L times t. Alright, so remember that this is the derivative of a product. That product is e to the R over L t e and this is equal to b of cosine omega t e to the r over t L. We will take the integral of these two equations. We have e to the r L t. Let me see if you can see this. Well, yeah. Alright, yeah. This is equal to, here we are taking the derivative, the integral with respect to the current, with respect to time. So here we have the integral of this stuff. I have b o l e e to the r l t. The integral of this stuff. This is the integral of cosine omega t e to the r over l t. Here the trick is cosine omega t. Let me write it as e to the omega t I, because this by Euler's identity would be cosine omega t. It would be cosine omega t plus I sine omega t, and we could use do everything with this, substituting this cosine omega t, and we could just take at the end the real part. So here I would put e to the omega t I, and so here I just have the integral now of this part. Is the only part that has I have, well, let me put this first. Integral of e to the r over l plus omega I, and all this times the time. Yeah, so now I can take the integral. So I have, here I forgot to put my I. So I have I e to the r over l t is equal to just b over l, and the integral of this is, I copied, is e to the r l plus omega I, this times t, and I divide by the inverse of this. So I have r l omega e plus some constant c, very big. So I have it like this. Let me multiply everything by L, yeah, L over L, and let me divide everything by this factor. So I would have I is equal to B L, this 10 L times L. Let me put it like this. I will make use of this later. E to the omega I t, and then divided by R over L plus omega I. So here I have I is equal to this L will cancel, and so I have B O e to the omega I t divided by R plus L omega e. This is what we get from the integrating factor. Now we will use either the Cartesian way or the polar way. The Cartesian way is to multiply this by the complex conjugate of this complex number. So we multiply this by R minus L omega I, R minus L omega I. So I have that the current is equal to B R minus L omega I divided by, this is R square. I square is -1, then this negative is plus L square omega square, and then times e to the omega I t. Alright. Remember that omega I t, e to the omega I t is Euler's identity, so now I will substitute this by cosine omega t plus I sine omega t. So times cosine omega t plus I sine omega t. And we said that at the end we will just take the real part. So what is the real part of this? Is just multiply the real parts and the imaginary parts, but not this imaginary with this real, because that will give me an imaginary part. So I will just take from now the real part. That would be, I don't know if you see from here. Alright. Alright, so I have I is equal to B O over R square plus L square omega square times, now I have R cosine omega t. Again, I times I is -1, because I is the square root of -1, times the negative makes it positive, so it is positive L omega sine of omega t. Remember that A cosine of omega A cosine of omega t plus B sine of omega t, or theta, or whatever you want, this is the same as C cosine of omega t minus phi, phi being just another angle. And this C is, if we have a right triangle here, we have this capital to be A and this B. C would be this. So C is the square root of A squared plus B squared. And phi is this angle. So tangent of phi is B over A. So I can write this as voltage over R squared L, you see it? Yes. L square omega square C. So C would be C would be the square root of R squared plus L squared omega squared. So here I have C, the square root of R squared plus L squared omega squared, and then cosine of omega t minus 5. There. So here we have this quantity is just the square of this quantity. So we could say that the voltage, that the current, this current is equal to the voltage over the square root of R squared plus L squared omega squared times cosine of omega theta minus 5. Being tangent of 5, tangent of 5 being omega L over R. So now this is the solution to the differential equation of a LR circuit with alternating current from the Cartesian way, and now we're going to do it in the polar way. So I will continue from here. That this was when we end with the integrating factor. So very quickly, we have this is a complex number. We can represent any complex number. Here we have a plane, the complex number plane. We can represent it. This is a point. This point is this R plus L omega I. This can be represented as some number A e to the to this angle 5 e 5 e, yeah. So this A is this magnitude, the magnitude. So if I have R here and R L omega here, I have that A is equal to the square root of R squared plus L squared omega squared. Phi is here we have I would be equal to VO over this, because this is the complex number, so over R squared plus L squared omega squared. And now this e to the phi I, here I have e to the phi I, that passes to the other side as negative e, as e to the negative phi I, and e omega I t. Yeah, for that. So this is equal to just e to the omega t minus phi I. And by Euler's identity, I have that the current is equal to the original voltage times the square root of R squared, L squared omega squared, and this would be cosine of omega t minus phi plus I sine of omega t minus phi, but we will just take the real part. So from the Cartesian way and the polar way, we found the solution to the differential equation for a LR circuit with a alternating current. That is the original voltage over the square root of R squared plus the self-inductance square, the angular speed at which we are changing the alternating current square times the cosine of omega t minus phi. This, in order to find phi, we have that the tangent of phi is equal to this quantity, that is omega L over